Hello, everyone. Good afternoon and good evening to those joining us for the session 1 of BSO 2022, which focuses on energy. My name is Ruqayya Aslan. I'm an associate professor at UCL Institute for Environmental Design and Engineering, and my research very much looks at how we can upgrade the energy efficiency of our homes. And I've recently started looking at the Global South as a focus. So this session is of both personal relevance to me and I think great importance for everyone working in our field. I'll be your session chair for this session. I know many of you are joining us online, and to manage the day today, we will have 5 papers from various speakers around the world. Some of them will be video presentations and others will be presented live. For every single presentation, regardless if it's a video presentation or live, they will last approximately 10 minutes, and we will have 5 minutes for Q&A following the presentation of each paper. So if you do have questions that come up during viewing or listening to a presentation, please feel free to type them into the Q&A box of the chat here in Zoom, and I will be reading them out. After we finish our presentations, we'll hopefully have some time to reflect on some of the key learnings and to have a debate about what was presented. So with that in mind, I'll move on to our first presentation of the day from Yashima Jain, who is representing a large team from the Indian Institute for Human Settlements and India Infoline Finance Limited, who have worked on a very interesting study titled A Demand Response Implementation Case Study for Islanding of a Building. So I'll hand over to the IT for playing the presentation.
Hello, everyone. Today, I will be presenting the work done on the demand response implementation case study for the islanding of a building. I am Yashima Jain, and I work with the Indian Institute for Human Settlements. The co-authors on this paper are Prasad Vaidya, Amit Chandra, Gopi Krishna, Uttej T, and Dismaya Paralkar. This paper is about a comprehensive case of planning, implementing, and testing an islanding use case on a 450 square meter mixed-use building. Now, when I say islanding, it means that grid power is not available and the building needs to suffice its needs purely on on-site renewable production. This islanding use case was implemented with an open source operating software to monitor and control energy systems on this prototype building. A little bit about this building. So this building is part of a campus that embodies experimentation and mainstreaming of zero carbon and resilient development. It is a 450 square meter building with 2 stories. It has an office and an environmental lab. The envelope is super insulated with efficient lighting and equipment. There's a PV array of 6 kilowatt peak and battery of 14.4 kilowatt hours. There's also a weather station mounted on the roof, and there is sub-metering that has been done at both the floor level and end-use level. Also, energy demand can be controlled at a granular level, so we can control energy at room level, end-use level, as well as floor level. A little bit background about this study. So we all might be aware that India is on a path of major growth in renewables against the target of achieving 175 gigawatts of renewable energy installed capacity by 2022. A total of 114 has already been installed as of June 30. This kind of penetration of renewables and an evolving demand of energy will lead to the formation of duck curve eventually. Now, in developed countries, this problem has been tackled by using demand response and storage, and it has become an important part as a solution. But integrating this is definitely hard to achieve and challenging. It requires aggressive and intelligent power management along with real-time prediction of on-site renewable energy. And that's what we have done with our work but at a very granular level. I'm sorry. I am now going to talk about the different steps that were taken to do this and the results that we achieved. So the first step was the energy audit. We did an extensive energy audit to compare building loads with photovoltaic generation and understand the end use, spatial and temporal energy use in the building. All operational power was measured. So for all equipment, light and fan, we've measured operational power to understand the building loads. Now, the comparison of the operational loads to be supported by the PV system gave the demand profile of the building when there is no grid power. The result was that building operations need more energy than that generated by solar PV array. That's what we found out. And the results helped us identify that we need to do intelligent demand response to be able to cater to our energy demand. And definitely equipment load proved to be a big guzzler. And the graph that you see on the right shows that on an average summer or winter day, generation is way lower as compared to the actual consumption in the building. And if the lab is running, then it goes beyond 10 kilowatt also, during summers. So that's what we found out using the energy audit. The next step was to create critical load scenarios using the energy audit data and historic solar radiation. So load profiles defined critical functionality, and the idea was to create multiple operational scenarios to island the building in the absence of grid power. Inputs were taken from facility managers and users of the building to understand their requirements. The results. So we created 5 bins ranging from 15 to 35 kilowatt hour to create these operational scenarios. These bins were based on the annual solar radiation data, and the table on the right shows the number of days under each solar radiation range. For example, there are only 9 days when solar radiation is less than 15 kilowatt hour, whereas there are 47 such days in the year when it is between 30 to 35 kilowatt hours. Now, these 5 ranges also helped us define the operational scenarios, which were red, orange, yellow, green, and blue, where red was the most critical scenario, where only critical equipment like IAT and IoT was allowed to function. Now, since the equipment was a big energy guzzler, and that's what we found out from the energy audit, we managed equipment load by cycling them through the day for different kind of uses in the building. Additionally, fans were also provided for thermal comfort in some scenarios. The graph that you see on the right is how we looked at the loads at an hourly level. So this graph is for one day or 24 hours. The green shows the photovoltaic output, red shows the actual building load on that particular day, and the yellow shows the battery status. So the aim was to not let the battery drain down to zero. That would lead to an absolute shutdown of the building. So the loads were managed based on the solar radiation for a certain day and respective production and battery storage. Now, the next step was to design the control architecture for this system. It was designed to be a distributed system with multiple layers in it, and all the sensors and microcontrollers were integrated in the hardware layer, which used Ethernet, Wi-Fi, or LoRa communication with the hardware. All recorded data was passed through cleaning scripts and then published to Kafka framework at the local server. The central server was maintained for high computational processing like artificial intelligence modeling and analytics. Coming to the results, so the decision of implementing a distributed architecture helped us to take edge decisioning independently at the local server. The combination of Apache Kafka and MQTT proved to be a good combination for various IoT use cases. And this allowed us to process data in motion and not just restrict it to a sub-messaging level. This approach and the use of open source technology made the operating system scalable and extremely cost effective. The next step was software integration, and this was where step 2 and 3 were actually integrated. So this led to the development of the operating system, where we had to align the operational scenarios from step 2 with the controls and relay architecture in the building. A part of this step was also to develop the user interface of the operating system. So the aim was to have an hourly level toggle for the 5 operational scenarios across different end users as well as spaces. Coming down to the results, so control at an individual equipment level was planned, but we did not implement it since it was not a scalable solution. We did control some high energy consumption lab equipment. Everything else was controlled at a floor level or room level or an end use level. This included fans, lights, ACs, as well as equipment. Now, the controls required us to set up frequency of cycling of loads for the 5 scenarios to enable power sufficiency for each typical solar day. The image on the right depicts the user interface at the maintenance side that also shows the granularity of the controls developed to operate the scenarios. Coming to the last step was the actual validation of all this work done, and we did that via actual testing in the building. So as part of our methodology, we had set up protocols to test the functionality and validate the correctness at an hourly level. The plan was to shut down grid power intentionally and let the OS take over and make decisions. So the OS would actually decide what operational scenario should the building go into. This was, of course, based on forecasted solar generation for that particular day. Now, the testing has been done twice so far and has proved to be successful, where the OS allowed the building to function based on the selected operational scenario and lasted for an entire working day. In one of the testing, the OS shifted the building into a green mode, where equipment functioned on cycling basis for various uses as well as spaces. A combination of PV generation and battery was able to sustain the building functionality throughout the day. The testing was done at an hourly level, where we logged the functionality of all end users and checked for its alignment with the designed operational scenarios. This was also a validation for all our controls and their functionality. During the testing, we also found out that the forecasted prediction will not always be aligned with the actual situation on that day. In one of our testing, the historic data showed that it will be a cloudy day, leading to a low PV generation, moving the building to an orange scenario, whereas it was a bright sunny day that day with a capability to operate in a green scenario. So we were able to actually identify the unreliability of historic data to predict PV production at an hourly level. The testing also involved getting feedback from the occupants of the building, and the occupants had been experiencing power outages during office hours, which made their working conditions quite difficult. With the implementation of this use case, it made it easier for them to work through these power outages, and the implementation of the islanding use case was actually appreciated by the occupants of the building. Concluding this work, so design and implementation of the DR for an islanding use case helped us actually demonstrate that it is technologically possible to combine PV protection, battery storage, and demand management using off-the-shelf relays and our campus operating system. Now, to make the solution scalable, controls with relays need to be done at room as well as zone level, and not at a level of workstation or a bank of workstation, since furniture arrangements may change in the future. So this will help to optimize the number of relays and also the complexity of controls. However, large consuming equipment must be controlled individually. There were also initial concerns by users about an automated system taking over building controls, especially plug loads. But during the testing, users actually realized that a planned switch to PV supply in a grid power failure scenario is better than an unpredicted power outage. This approach to DR is more aggressive than found in our literature review, where we aim to control and cycle power available to outlets for users. Now, in an islanded scenario, initial results say that the level of DR seems acceptable to users. However, more rigorous user acceptability testing needs to be done. Also, as a next step, we are exploring, since we've identified that PV prediction or has not been very reliable, we are working on AI models and machine learning to be able to predict the actual solar generation and radiation based on the historic data that we are recording. So the last 30 days or last 40 days, that data we are using to actually develop a model for better results. And that's all for my presentation today. Thank you for listening, and I'm open for questions now.
Thank you very much, Yashima, for such an interesting presentation. I'll be monitoring the Q&A section, so please, if anyone does have any questions, please do post them there. We'd be more happy to share them with Yashima and get some of her feedback on any queries you might have. But while we wait for those questions to come in, Yashima, I have a question myself, and it concerns the title of the paper. The term islanding, you described what it is, but could you shed more clarity on why does islanding happen?
Right. So islanding happens when the grid power, which is coming from a nearby thermal plant or nearby, that's what the service in that area provides. If that gets disconnected, that's the scenario when you have to be in an islanded mode and suffice on the generation or storage that you have in your building. And I think that's what islanding is. And with respect to this site, there has been very irregular power outages for very long periods, which definitely made it difficult for the people working in that area. And that's where this has proved to be helpful, where they are able to function even when grid power is not available.
Thank you so much for that explanation. Yeah. It's absolutely fascinating as a phenomenon. We have a question from the audience, which is asking, how was the user concern regarding the automated takeover address? And to be honest, this is a question that I wanted to ask myself. What was the appetite as well for demand response within the context?
Right. So initially we did get some like negative feedback on if power is being controlled by something external. So there was reluctance with respect to that, but during our testing we did find out that users were more acceptable and understanding that okay, there might be scenarios where we are not able to work at all, but this current situation, the islanding, is helping us actually work and complete our tasks for the day or whatever it may be. So I think overall the user concerns I think were addressed during this testing, but as I said, more rigorous testing needs to be done to be able to understand what the users actually feel, because this was like on a conversational basis. We did not actually do a survey to understand. So yeah, this was very initial feedback that we got.
Thank you very much for that, and thank you again for your excellent presentation. I think, let me just see the Q&A. We have another question from Robert McLeod, and the question is, does it not make more sense in practice to cluster multiple buildings together to create a larger island and achieve better load diversity and flatten peaks? And he also is asking, have you looked into these aspects of optimum island size as well as part of your research?
Right, that's a great question. Absolutely. I mean, that's the whole idea. So it's a large 55-acre campus, and this one building is actually the prototype building where we are testing multiple types of technologies, multiple types of ways of construction, and uh, if successful on this particular building, the other buildings that come up on this campus, we will be able to then implement and as mentioned in the question, load diversity and flattening the peaks. I think all of that will be possible once these other buildings will come up. So yeah.
Thank you so much, Yashima, for answering each and every one of these questions so eloquently and decisively. I'd like to invite our next speaker and IT to run with their presentation. So our next presentation is going to be presented by Srijit Jayaram, who is representing a team from the Indian Institute for Human Settlements and the Alliance for an Energy Efficient Economy. And the paper is titled The 12% Effect, Improvements in Evidence-Based Design Towards Net Zero Building Performance.
Good morning or evening, depending on which part of the globe you are in. Our paper is titled The 12% Effect, Improvements in Evidence-Based Design Towards Net Zero Building Performance. Our paper is about analyzing the student work in an educational program that builds capacity towards net zero. I'm Srijit Jairam, the presenting author for this paper. I'm an associate working with the Sustainable Energy Lab with the Indian Institute for Human Settlements. My co-authors are Amanda Thanajam, Gaurav Vakil, Janani Venkatesh, Suyashi Srivastava, and Yashima Jain, who are from the Indian Institute for Human Settlement and the Alliance to an Energy Efficient Economy. We are all here to address one common problem, which is climate change, and there is no need for me to emphasize on the urgency for us as a global community to address this problem. Especially in the global south, we are more vulnerable to the impacts of climate change, and our efforts need to be stronger. India is the third largest emitter with 7% global emissions, and at COP26, India set the Panchamrit goals to achieve net zero by 2070. This year at COP27, India has launched the In Our Lifetime campaign, which will recognize youth between ages 18 to 23 to become message bearers of sustainable lifestyles. In addition to the climate goals set by India for 2070, it is also predicted that India will add about 40 billion square meter of building area by 2050. These can be designed and built as net zero energy buildings. The graph shows the total floor space that will be added over the next 3 decades in teal, and what we can expect with regulation with a best case compliance in green. Uh, However, this requires a net zero capable workforce that grows at 10% per year for the next 3 decades, and this is a huge gap. This net zero capable workforce will need to be trained in building performance simulations, or BPS as it's commonly known, in order to provide grounded evidence based designs to achieve our ultimate vision of net zero. Training programs for building performance simulation have not captured the imagination of students or professionals to get them excited about the race to zero. We are attempting to address this gap in BPS education through the Solar Decathlon India program. And it is a competition for collegiate students to design net zero energy and water buildings. They work on live projects by partnering with real estate developers in the country. Across the 2 years, Solar Decathlon India saw 2,200 plus students who participated in the program who partnered with real estate developers. The authors analyzed the work done by the finalist teams of both years. The teams worked on 10 contest areas and hence the term decathlon. They had to do well across all contests to win. In order to build the capacity for the teams to be able to design net zero energy projects, The SDI program provided them various resources such as the 10 online self-learning modules and webinars which mirrored the 10 contest areas of the competition. We gave them simulation software and calculation tools for costing and water consumption. And from the learnings of year one, the program provided BPS training to the teams to enable the teams to provide evidence-based designs. The teams had access to a technical resource group, which is comprised of young professionals working in the industry. The real capacity building happens when the multidisciplinary team is able to apply these learnings to a real world problem which they worked on for the competition. At the end of the finals, the authors wanted to know how well these teams were able to produce evidence based design. As part of our analysis of student work, we wanted to know whether teams proposed energy conservation measures for their project, and importantly, we wanted to see whether the student teams were able to provide evidence in the form of simulations for the strategies they were addressing. This is an example of some of the student work in year one and year two. From our study, we found that most teams claim to integrate ECMs, which are typically included in high performance building design. However, some teams did not provide evidence to support their claims. Maximum teams showed optimization of wall and roof assemblies followed by fenestration optimization. We did a detailed analysis to look at the work produced by the students, which we will see now. Comparing the 2 years, we found that in total, about 86% of the teams proposed ECMs in their designs. Similarly, there were about 12 to 21% more teams who provided BPS as evidence for strategies related to building envelope, which includes optimization of wall roof assemblies and shading. There were 10% more teams who presented BPS as evidence for passive design strategies such as form optimization and orientation of their building design. There was a drop in the number of teams who provided evidence for window to wall ratio optimization of the building envelope. The percentage of teams providing evidence for HVAC strategies were roughly similar in year one and year two. And the natural ventilation strategies, which had the least number of teams providing BPS in year one, we saw that there was an 18% increase in year two. Overall, on average, there was about 12% more teams who provided evidence in the form of simulations for their proposed designs. There were some interventions and improvements that the organizers made in year two, which may have yielded these results. Many of the areas of studies are new to the team and they're not part of their existing curriculum. The teams were not aware of these topic areas and found it difficult to provide evidence. The teams may have had difficulties in receiving training in building performance software. For year two, we included a 5-part simulation training program and faculty development program as part of the program schedule. We refined the requirements of the competition and we made them more comprehensive. Even though the organizers made improvements, a bigger change would be needed to have a larger impact. In India, the national statutory bodies which govern the technical education curriculum offers courses on climate analysis, passive design, and energy efficiency to architecture and engineering related coursework. However, these are not mandatory and these are not comprehensive as well. Specific coursework related to building performance simulation for energy, thermal comfort, daylighting, artificial lighting, and natural ventilation are not offered by the curriculum. As organizers, we look to further work on policy change for education and for market transformation in the building sector. Comparing the student work in year one and year two, the program was able to see a 12% increase in evidence-based design by about 2,000 plus students. Bringing about a curriculum integration of the program can definitely amplify this impact. The national statutory bodies will need to formalize BPS education to be able to do this curriculum integration. In the coming years, the organizers are looking to identify gap areas so that the teams will have access to more resources and better BPS education to help them arrive at evidence-based designs. The next generation will need to be prepared for the clean energy transition as well as for adaptation. Thank you. And that was the end of my presentation. I would like to thank the organizers for giving me this opportunity to present. And I would also like to thank my co-authors who have also worked on this paper extensively. Thank you.
Thank you very much, Srijit, for that very insightful presentation. We often look at the outcomes of building performance simulation and its impacts on design, but it's really insightful to have a study that looks at what it takes to build up skill sets in this area for it to happen. So excellent presentation. Thank you very much. And I'm sure it will be of immense interest to both of us working in education, academia, but also to developers of software as well, trying to integrate them within sort of the educational process. A reminder to attendees, there is the Q&A portal available for you to post your questions. I'd be happy to pose them to the authors today of our research papers. But while we wait for those, I have a question for you. So in terms of the makeup of the teams, they were mostly students. Can I ask, did they have different skill sets, or did they come from different educational backgrounds that led to them being on this course? And did sort of the makeup of the teams reflect reality in terms of what you would be getting in a professional setting?
So we predominantly had students participating from the architecture coursework and also engineering coursework. So there was a mix, and we tried to keep it as a mix. We try to keep it as a multidisciplinary team because that's how the real world functions, right? So we want to do that as much as possible. So every team which has a set of architects, we say that there should be at least one engineer in your team. Similarly, if there is a group of engineers who are coming to participate, we say there should be at least one architect in your team. So that's how we have been sort of balancing out the team composition. Yeah.
Thank you so much. We have a question from the audience from Isha. Isha, thanks you for your presentation. And her question is, was the increase in certain factors or areas in year 2 affected by the winning entry for year 1? So did people look back and see what worked and try to implement it in their own designs?
Possible, because we did give the final reports that the winning entries to the next year students, so that they could refer back and see what kind of work was already being carried out. So that's highly possible, yes.
Okay, well, I think it's good to have those learnings out there for people to benefit from.
Yeah.
I have another question myself. Based on this study and your expertise in this area now, what would be the main 3 priorities for curriculum development to inform evidence-based design going forward? Top 3 recommendations.
I think for sure policy change is definitely one. The curriculum itself needs to realize that this is really important, and I think awareness is another one. We need to sort of tell the students who are coming into these coursework that net zero, about we need to talk to them about the net zero goals and the larger vision of all of this. Yeah, I think it's just 2 for me right now. I don't have anything else to add on that.
I think that's more than enough. Thank you so much, Srijit, for your insightful responses and for taking the questions. May I suggest that we move on to our next presentation, which will be given live, I believe?
Yeah, that's right. I'm going to try and share the screen, so tell me if it works.
Okay, so I'll just introduce you first. We are honoured to have Professor Rajat Gupta from Oxford Brookes University, who will be representing a team both from his institution and from the CLASP India programme and Environmental Design Solutions PVT Limited. And their study is titled Examining the Variation in Daily and Peak Electricity Use in Urban Indian Households by AC Ownership. And Rajat, I could confirm we could all see your presentation.
Brilliant. Thank you, Kian. Thank you for the introduction as well. So what I'm going to do is I'm going to, of course, present this live and talk a bit about the work we are doing as part of a larger Indo-UK project called Reside. And here we kind of focus on data set that were provided to us by CLASP India and the Environment Design Solutions. And the focus really is to look at what is the variation in daily and peak electricity use across a small sample of urban Indian households by extent of AC ownership. So what happens if you have one AC unit versus two, and what are three or more? So just to give a bit of research context, residential electricity use in India is expected to increase 5 times by 2032. This is, Bureau of Energy Efficiency's estimate. We also know that cooling demand is mainly coming from room air conditioners, which is the key driver for residential electricity use in India. This is happening despite a couple of facts. First of which is that India has one of the lowest access to cooling across the world. While per capita cooling consumption is just under 69 kilowatt hours against a global average of 272 kilowatt hours. And this fact was stated by one of the keynote speakers as well. And also, India has the highest distribution of cooling degree days anywhere in the world, which means that this is likely to increase with a warming climate. So the situation is only going to get worse from climatic point of view. At the same time, it is predicted that air conditioner sales are going to explode from 42 million 3 years back to about 240 million. That's a lot of increase, just under 7 times. So clearly, there's going to be a significant rise in residential electricity use in India. And it's very important and probably necessary now to examine the pattern of residential electricity consumption, not just from models, but from actual empirical data to really identify what are the peak periods of electricity use, so we can develop measures to either reduce its use or at least manage it so that we don't cause brownouts and blackouts. So what we did here was we conducted statistical analysis of high resolution time series data on electricity use. Essentially, we looked at a variation in daily and peak electricity use by seasons, so summer and monsoon. That's because that's where most of the air conditioning is likely to happen. Weekdays, weekends, and most importantly, extent of AC ownership. So the sample was broken into kind of 3 groups of households, those with 1 AC unit, 2 AC units, and 3 AC units or more. And the sample size was about 54 urban Indian households. And you can see the split. And the study is really part of this wider 5-year project called Reside, which is with colleagues in MNIT Jaipur and IIIT Hyderabad. And there's a whole website. So, and I think we're going to talk about some of these projects tomorrow. So the study sample was really, based on the data set provided to us by NEEM CLASP. And the households were located across 3 climatic zones where air conditioning use is dominant. So this is the composite zone here, the warm humid zone, and hot dry. And that largely covers most of geographical India. There's obviously the cold zone where hopefully we don't have that much air conditioning, and a little bit of temperate zone. 70% of the households in the sample were located in the composite and warm humid zone. So somewhere there, the remaining 30% were in hot dry. In terms of size of households, they were between 50 to over 100 square meters, 30% less than 100, 30% just over 100, and the remaining 50 to 100 square meters, which is similar to other kind of studies done nationally in terms of the size of households. In terms of methods, so we had time series data collected every 30 seconds between Jan to November 2018. So this is pre-COVID, so we didn't have that influence of home working yet. And the data that were collected included electricity use, peak demand, power factor, voltage, and frequency. And then we conducted cluster analysis using K-means to identify typical profiles of electricity use as well. We presumed that the summer season, which you can imagine, India being a vast country, can differ a bit, but we had to make some kind of presumption, and we assumed it was essentially the drier season, April to June, and then the monsoon season from July to September, where obviously humidity is high, but ambient temperatures are slightly lower than summer season. The dominant form of air conditioner unit that was present in the sample was a split unit. It was about 1.5 tons and 3-star rated. And the amperes that it has is 7.628 amperes, which we kind of assumed to predict the air conditioning usage. And essentially, we looked at the compressor on-off cycles, and by locating those events within the electricity current, we could predict when the current increases above the rating of a 1.5 ton air conditioner. For over 30 minutes, we knew that the air conditioning is coming on. And then we kind of automated that process for the entire kind of data set. So you can imagine there was a lot of data to kind of look at. I'll go into the results bit because I guess that's of interest. So just to kind of look at the variation in annual and seasonal electricity use, what was evident was that there was variation as you move from homes with one air conditioning unit to 3 or more. And that became obvious whether you look at, mean annual electricity use, where you can see it goes from 3,500 kilowatt hours to 5,500 kilowatt hours for 3 or more AC units, or whether you look at mean daily electricity use, where 19 kilowatt hours for 3 or more ACs is double that of one AC household, or even when you normalize it by area, you get very similar kind of results. And that happens, as you can see, in whether you look at summer and monsoon season combined, or summer or monsoon separately. Most of these households had higher AC usage during the weekend, and the daily hours of AC use in households with 3 AC units was almost double that of one AC. And most of the peak electricity use was during nighttime, and I'm going to talk a bit more about that in one of the slides later on. When we talk about air conditioning, electricity use, firstly, the summer and monsoon seasons accounted for about 60% of the annual electricity use. So you can imagine that this is a major kind of period of electricity usage. And the air conditioning use in households with 3 or more AC units was about 43% of the summertime usage, and was about 34% in the monsoon season. Slightly lower, as you can see, in the 2 AC households and 1 AC households. So you can actually see that as India starts to urbanize more and multiple air conditioning units tend to get installed, the situation is going to get much worse. For the moment, there is no centralized air conditioning in homes. Majority-wise, it tends to be room-based. And again, the mean annual contribution of AC use as a proportion of annual electricity use, as you can see, for the entire year is about 10% in 1 AC household, increases to a quarter, 25% in 3 ACs. So there's a big difference as you kind of have more AC units. We then plotted the entire data set, essentially, looking from April to September, just to look at, how was electricity use overall varying. What was the air conditioning use in a 1 AC unit dwelling, 2 AC, and 3 or more. And then we wanted to see, for how much time air conditioning had been used in these 2 seasons, and it was up to 38%. So there's a significant amount of time. And what is interesting is that daily electricity use and proportion of AC use is higher in the summer than monsoon season. The reason I say that's interesting is because in the summer season, which is more dry, you could have other means of providing comfort, like evaporative cooler, for example, because you don't have that much of humidity levels as compared to the monsoon. So there are areas of kind of saving energy there. Then when we look at proportion of AC use against daily electricity use, so that's the amount of AC that's used over a day, especially with households with 3 or more AC units, it can go up to 50%, as you see here. In some cases, it's going up to 50% if you start reading of this, as compared to those with 1 or 2 AC units. And the maximum daily electricity use in 3 or more AC unit households goes up to 30 kilowatt hours. If you read off this y-axis, you can see that which is double that of 2 AC and 1 AC units, which stays around about 15 or under. And then when we started to look at daily electricity use profiles, because you want to see what kind of magnitude of electricity use happening and when, And as I said, peak electricity use were observed to happen during nighttime. So that's essentially for sleeping purposes. And air conditioning, if you look at these three lines, so there's for one AC dwellings, these are two, and these are the ones with three or more. So although they have a similar trend, you can see there's more frequently AC used in dwellings which have three or more AC units. And when we start to look at what is the amount of electricity used during the peak period, in three or more AC unit dwelling, it's about 6.3 kilowatt hours in that peak time period. And I'll just tell you what that peak period was. Versus 4.6 kilowatt hours in for the two AC units and one AC unit dwelling. And the most frequent usage of AC was recorded in the nighttime from 8 p.m. to 2 a.m. And that is for overnight, of course, and also late evening activities. And if you look at this table, for example, which kind of clearly shows that this is 8 p.m. to 2 a.m. is really the peak period of electricity use, largely for air conditioning. But there is also an afternoon period where this is air conditioning is used, and that's probably for resting purposes. We also kind of then ignored 1, 2, and 3 AC kind of groupings and just took the 54 dwelling sample and applied cluster analysis just to see what kind of clusters we get and will they be different in terms of their indoor electricity use profiles. And actually they weren't. So, two clusters emerged based on the analysis. And again, they have very similar profiles in terms of late night peak period. So essentially that provides an opportunity for some management of air conditioning in smart ways to reduce its usage. What is interesting is as cluster 2 had mostly 3 or more AC unit dwellings, and there the magnitude is much higher than cluster 1 in terms of how much electricity is used during the peak period, and you can see that here. And in fact, you can see the daily mean electricity use of cluster 2 is pretty high. It's around 17.3 kilowatt hours to 11.6 in AC cluster 1. So the point really is that even if dwellings are air conditioned, within that grouping, you can have a lot of variation depending upon the number of air conditioning units that are present. So what are the key findings and what are the implications of this? It's very data intensive, and obviously there's a lot of data crunching going on. But what are the key takeaway points? I think first is that, of course, seasonal differences matter in India, and summer and monsoon season contribute to about 60% of annual electricity use. We also know that AC usage in these seasons contributed to around 25% of annual residential electricity consumption, and about 50% of daily electricity use, in some days. The extent of AC ownership matters because households with 3 or more AC units can have double the amount of daily, seasonal, or annual electricity use as compared to one AC households. And that's I think is a really interesting find because most of the households will be progressing from 1 to more AC units. Similar patterns of AC use were observed in the summer and monsoon seasons for all households, irrespective of the extent of AC ownership. There is a nighttime peak, although the magnitude of that peak and the peak usage period, so it might be slightly longer in certain dwellings or slightly shorter, could differ by extent of AC ownership, but the trends remains the same. And as I said, it's mainly concentrated during nighttime from 8 p.m. to 2 a.m. with an hour of peak use in the afternoon in some dwellings. So what do we kind of take away from this? First is obviously there's a limitation that this is a study with a small sample size of 54, although the amount of data that's collected, I would kind of say it's very data intense and in depth. And it does show that if you increase number of AC units, there are huge implications for daily, seasonal, and peak electricity use, which has implications for the local electricity network. Some effort needs to be made to increase the use of desert coolers, for example, with fans possibly during the summer season where humidity levels are lower, and that could reduce the usage of air conditioning, especially in homes where there are 3 or more AC units. We also know this is going to get much more difficult to manage because with increasing urbanization, home working as a result of the pandemic, and outdoor temperatures that may rise because of a warming climate that will lead to a rise in the number of AC units to achieve thermal comfort in multiple rooms. So essentially, it's no longer going to be just one living room or a bedroom. Multiple spaces might start getting air conditioned, and this is already happening. We've recorded about, I think, 10 to 12 AC units in one dwelling as well. So this is, getting to a point where it needs to be managed, because policy measures, could be targeted based on the extent of ownership of AC units, so that peak load management could be done through demand side response. So because some amount of air conditioning is probably going to happen, some smart and flexible AC use is becoming necessary. So managing air conditioning, in line with external weather, in line with grid signals, so that we can avoid blackouts and brownouts. And maybe the new generation of air conditioning units need to have the smartness inbuilt now alongside their Energy Star ratings. And without this kind of a robust demand side response strategy, which can either be driven by time of use tariffs or other DSR signals, maybe availability of renewables locally in the grid, it may be that the electricity distribution companies in India will need to make expensive and disruptive reinforcement to the electricity network. And that's something to be avoided. So I think if we can manage this smartly and flexibly and avoid the increase of number of AC units, and try and see if it can be between 1 and 2, that could halve the increase of electricity use that's expected in the next 10 years in India. Thank you very much. I'm going to stop because I cannot see anybody and I'm sure I've run out of time. I'm going to stop sharing as well.
Thank you so much, Rajat, for a fantastic presentation. We've already got quite a few questions from the audience, so I'll just jump to them. So you talked about urbanization, but what would you expect in terms of a pandemic situation and today's hybrid working scenario? And Isha is asking if you can just extrapolate based on your findings to that particular situation.
Yes, interestingly, the data that we have is pre-COVID. So, I wish we had, after COVID, it would show a very different situation. I think what's going to happen is, because people are now having home offices, where previously, when we were doing empirical work, we found air conditioner were either in the most occupied space or the space where people were sleeping. So, which obviously could be the bedroom. But now, because of a home office and because of the internal heat gains, more air conditioning is getting installed. And so homes which had previously 1 or 2 are now having 3 or 4, and both the husband and wife are working. So you might have 2 rooms with 2 more air conditioners, and they are all running simultaneously as well. So, previously I always found in India that even if a home had 7 air conditioners, at any given point, you'd only have 1 or 2 running. Whereas now the situation is changing. So the implication of that for peak demand management is pretty serious. You're going to have very heavy loads on the grid, and without any demand side management, I think we could see, too many blackouts or brownouts in future.
Well, thank you. It's both interesting and frightening to think that that might happen in the future. I have a second question here, which is, more of a reflection as well as a question. So Isha has said that she has often observed voltage drops in peak summer periods in India. Do you think that a differential pricing electricity model will help reduce electricity consumption?
Good question, Isha. I'm on a time of use tariff, so I understand, what it means, but it depends who it is for. If the pricing is not to a level where people are going to change as a result of that, then it is meaningless. I think it's got to be very carefully designed in the Indian context. Some amount will matter, like in UK now, as prices are pretty high and it's beginning to bite. People are willing to make changes on their own. I think in India, because the unit cost of electricity is still very low, the time of use tariffs need to be designed carefully. And maybe other DSR signals also matter. So not just time of use tariff, maybe because there is likely to be overloading of the secondary substation, there is more incentive provided locally by the discoms in India for some localities to be able to cut their demand. And in return, they're going to get other benefits, which could be vouchers or whatever they are. And I think that needs to be thought through in terms of other revenue streams that people might look at. So not just time of use tariff, but others as well.
Thank you very much, Rajat. I have another question from Sukumar, who asks, did you observe any difference between the less humid and more humid regions that you studied? For example, do coastal regions show less variation between summer and monsoonal periods?
Great question, Sukumar. I wish we could have done that. Our sample size became smaller and smaller as we kind of stratified our sampling. So we had 54, and then you had smaller for one AC and all. There was some difference, but because at the moment in the management of the AC is not in line with external weather and temperature relevant variables such as relative humidity, that difference is not significant. But my kind of point is that if the new lot of air conditioners are designed with that management so that they can be run in different ways, and certain set point temperatures cannot be reduced beyond a certain threshold, that could make a difference, and they could be then sold in regions where humidity is high or low, as the case may be.
And one final question, was occupant behavior a factor in the study, and can this be analyzed for insights?
I wish, Isha, it was a nationwide study. So the occupant behavior was included in the way survey questions were asked. So yes, but it wasn't picked up over time because we kind of didn't gather the data. It was gathered nationally. But obviously, if you look at the data, you can begin to see some effects of occupant behavior, where sometimes air conditioning is used only for 30 minutes or slightly more and then switched off. Whereas in others, you can see it's on from 7 o'clock in the evening to 7 o'clock in the morning. So it is there intrinsically. If you look at time series data, occupant behavior is very much there. It's a question of just reading it. So yeah, it's there, but we weren't collecting occupant behavior related variables.
Thank you very much for that, Rajat. A fascinating study, and we very much, all of us very much enjoyed that. Thank you for taking the time to present your very interesting research work. Thank you. And with that in mind, I'd like to invite our next speaker, Sabah Hajizada, who is representing a team from Ocean University. And their research is titled Sustainable Retrofit Solutions for Decreasing Energy Consumption of a Residential Building in Tabriz, Iran.
Hello, everyone. I'm really happy to be among you. Can I share my screen?
Yes, please.
Okay. I'm going to represent the sustainable retrofit solutions for decreasing energy consumption and CO2 emission of residential building in Tabriz, Iran, on behalf of a great team. Let's have a quick review of what is going to be represented. I'm going to start with the introduction. The rapid growth of Iran's population in the last 4 decades has caused many residential buildings. Energy in Iran is really cheap since Iran subsidies energy costs as well as water and electricity tariffs. Also, these subsidies are meant to lower the energy cost for consumers. They raise the energy consumption and usage. Therefore, the number of residential buildings is increased. The research objective of this study is retrofit a residential building in Tabriz, Iran, to show the importance of sustainable retrofit for decreasing building energy consumption and CO2 emission. Also, determine the most effective scenario to get the best result. To fulfill this research objective, 5 steps are needed. The first step is to determine the case study building and determine the climate conditions. The second step is calculate the energy performance of the RBs. We call RBs because it's a reference building, so we call it RB. In the third step, determine the scenarios, which is the combination of the single and combined scenarios. The fourth step is to analyze building energy retrofitting scenarios, and the last step is perform assessment analysis of the result. So let's look at case study. The case study is located in Tabriz in the northwestern of Iran, which has the cold and dry climate. The average daily temperature in summer in Tabriz is 27 degrees, and the average daily temperature in winter is equal to 8 degrees. And this is the residential building. It has 4 floors. Each floor has a 183 area meter square. And this case study was modeled with the Design Builder software. 4 scenarios has been considered. The first scenario is the combination of replacing single windows with double glazed windows and adding some shading elements on the south facade. The second scenario is about the replacing lighting fixtures with LED and apply some wall insulations. And the third one is about the applying PV panels on the roof and again wall insulation. The last one is the combination of all the above scenarios. Let's look at them a little detailedly. In the first scenario, we assume that the double glazed windows is replaced with the single windows glazed, and which has the 30 millimeter argon gas. For the shading elements has been located in the south facade with the 30 to 35 degree, which they work only on the summer period. In this second scenario, LED lighting fixtures has replaced with the simple incandescent lamp. As you know, LED lamp can save energy from 30 to 90%, and LED lighting is free mercury. So, and they generate less hot. So it's really good for sustainability. And for the external insulation, I would like to show you these figures. The left one shows the wall detail before applying insulation. The right one shows the detail for the after insulation. The insulation material is expanded polystyrene with the 10 centimeter thickness, which can save a lot of energy. Again, back the third scenario, which is the combination of PV panels and again insulation. I would like to show you the Iran's high potential to use PV panels. That's why we used the PV panels for this case study. 54 PV panels has been applied to this case study. The panel size and the information of the panels has been calculated with the PV Salt software. This is the result of the PV panels. In the left figure, this is the result of the case study before applying PV panels. The right one shows the power conversion of sunlight into the electrical energy, which is equal to minus 11 kilowatt-hour per meter square. Given that it's impossible to get the minus to produce a minus amount of energy, but it refers to the net energy building. Here is the result of CO2 for the reference building and scenarios. And as you can see, this third scenario and the combination, the last one, again, the amount of CO2 from the May to October is negative. Again, given that it's impossible, but it refers to the net energy building for the carbon. So by lowering heat loss, insulation reduces the demand for gas or central heating. Therefore, in any country, a good government policy strategy may reduce carbon emission at the building and urban scale. Here's the result. In the RB's column, we can see the total energy amount is equal to 153 megawatt-hour. For the first scenario, which is the combination of window and shading, we don't see that much, but it's good. But for the second scenario, which we got the best result, which is equal to around 60 megawatt-hour, we can say that it's a 65% reduction from the RBs, from the reference building. And the third scenario, which is the integration of PV panels and insulation, which is equal to 61, and the last one, which is the combination of all of them, is equal to 63. So the best one, we can say that, which is the integration of insulation and LED, and we can again see this difference from the natural gas and other routes. Here, the conclusion for this part. This is the primary energy, this table, and again, it shows the retrofitted scenarios results. And I would like to say that results shows that the use of these retrofit scenarios has a positive impact, considering that Tabriz is located in the cold climate and winter is really freezing in Tabriz. And in the scenario, in the second and third and fourth scenario, which includes external wall insulation, has the best energy consumption to reduce heat loss. Therefore, this research confirms that applying an external insulation layer can be helpful in the climate of Tabriz. For the future work, researchers can work on the cost analysis of these scenarios and also solar collector for the reduction of the hot water. This is my end of the. Thanks for your attention.
Thank you very much, Saba. It's always fascinating to see what retrofit looks like in different contexts, and your study has shed light on the Iranian context.
Yes.
And it's interesting to see that it looked at more of a cold climate in Iran, whereas most people would expect it to be hot throughout. Actually, the climate is very variable, so I think that's fantastic. I'd like to remind attendees to post their questions in the Q&A portal, but till then, I've got quite a few questions for you. So you mentioned that you used PVs as part of a couple of your retrofit scenarios. Could you describe what these PVs, the technical specs of the PVs that you assumed?
This is photovoltaic panels to produce, to convert the sunlight to the electrical energy. So we use these PV panels to reduce the energy for the building, for this building.
Yep. So what type were they?
I'm not sure that I catch the question.
What type of PVs did you use? I know there's some data there, but it's very, very small. So the parameters, if you could just shed more light.
Yeah.
If you could just shed light on them, because they're quite small, I can't really make them out.
Yes. Here, you mean?
Yes.
Here's some for the panel size dimensions and the distance of the panels that they are going to locate in the roof. And yeah.
Okay, thank you. Thank you very much. A lot of the work, I have another question for you, if you don't mind. A lot of the work today talked about demand side response. How do you see this strategy working with your retrofit scenarios, and also the fact that you are integrating renewable energy? How would that work with perhaps a demand side response strategy?
For this case study, and I work in Istanbul. So for the demand, I think if we consider good retrofit options, we can reduce the demand for the energy with some renewable, retrofit options. So it could be a good for some retrofit case studies.
Thank you. And I don't see any questions coming in because I think your presentation was very clear.
Thank you.
So perhaps I have time to ask you one more question.
Yes.
So you mentioned that Tabriz is in the colder part of Iran, and you with the implementation or with the execution of insulation. Have you thought about overheating risk in the summer as well?
Yes, it could be. Yes. And we for the cooling part, maybe we need to use more cooling equipments during the summer, but we just focus on the winter part because, in the summer we have another options, but in the winter we need to try to try to save the energy inside of the building.
Thank you very much, Saba, for that.
Thank you for your attention.
We've not received any other questions, so may I suggest that we move on to our final presentation for the day, and thank Saba for her amazing work. Thank you.
Thank you.
So our final presentation for the day will be a video presentation, and Xiliang Yang will be representing the team from the School of Built Environment Engineering and Computing from Leeds Beckett University here in the UK. to speak about a study titled The Energy Performance Assessment of Gas Boilers, Air Source Heat Pumps and Insulation Type Pairings in UK Dwellings.
Good morning, everyone. My name is Siliang Yang. Thank you for giving me this opportunity to do the presentation about my research on energy performance assessment of gas boilers, air source heat pumps, and insulation types Pairings in the UK dwellings. My presentation will cover the introduction, research aims, research methodology, results, discussion, and conclusion for the research study. Now I'm going to talk about the details. Basically, in the UK built environment, about 48% of carbon emissions come from the existing housing stock, and 62% of this is from heating. To meet the UK government's commitments to net zero carbon by 2050, the way homes are heated must be changed from current conventional means such as gas boilers to more sustainable methods such as heat pumps. The use of heat pumps in dwellings can look to significantly reduce a household's carbon emission from heating, as well as help reduce running costs significantly. In terms of heat pump technologies, air source heat pump is proven to be an ideal option for dwellings than other heat pump types due to its accessibility, lower life cycle costs, and high efficiency, which has been promoted by the UK government's boiler upgrade scheme. However, air source heat pumps efficiency tends to decrease during a period of severe cold. For instance, when the ambient temperature drops to 0 degrees Celsius, and therefore weakens its heating performance. Consequently, the building fabric certainly will need to compensate for the loss of thermal heat. However, according to the Housing Survey of the UK, 20% of housing stock in the UK is more than 150 years old, and 40% was built before 1944, which comes with less insulation leading to heat dissipation through building fabric quickly. Therefore, it is crucial to have a massive program of retrofitting the dwellings to prevent heat wastage. So, it is pretty clear that the gap between the adaptability of air source heat pump and uninsulated homes should become the focus of research within the built environment, which has sought to explore the possibility of a balanced solution. However, questions still stand on if a sustainable heat source is sufficient alone to reduce a household carbon footprint without an adequate insulation of building fabric. Therefore, this study aims to investigate the benefits and the drawbacks of different insulation types of typical UK dwellings when paired with conventional gas boilers or air source heat pumps for reducing domestic heating energy demand and carbon emission and improving energy efficiency and overall feasibility. This study, however, will serve as a role model for the synergetic research and development of low-impact domestic HVAC systems and housing retrofits within the global context, within the global south context, in response to environmental deterioration. In terms of the research methodology, this study was based upon simulation modeling using IES. Basically, 3 separate heating systems and the building fabric insulation pairings were used to provide different systems characteristics and admittance properties for a case study dwelling of 2-bedroom bungalow in London. Specifically, the 3 scenarios are gas boiler with adequate insulation, air source heat pump with adequate insulation, and air source heat pump with inadequate insulation. Typical construction design options, including the thermal properties of the 3 dwelling scenarios, were used within the IES models. Due to the time limits, other information of the simulation modeling are not included in this presentation, but all the relevant data has been specified in an accepted conference paper. All the results of the proposed study were based on a full year cycle for the three aspects: total system energy consumptions, total system carbon emissions, and external wall transmitted heat losses. Regarding the total system energy consumptions shown in the figure, both air source heat pump scenarios showing a significant reduction in system energy consumption in winter months in comparison with the gas boiler scenario. With air-cooled installation, the biggest disparity was found in January, in which the air source heat pump was about 53% more efficient than that of the gas boiler. A similar significant increase of 26% efficiency was shown with the air source heat pump with in-air-cooled wall installation in the same month, which, however, demonstrated the benefit of air source heat pump in minimizing energy consumption and is considered more sustainable. The results of the system carbon emissions show similar trends as the system energy consumptions. As can be seen in the figure, the adequately insulated building with air source heat pump system had the lowest carbon emissions over the winter months. The highest reduction of carbon emission using air source heat pump in comparison with gas boiler was around 44%, which is equivalent to 291 kilograms carbon dioxide, which was found in January, while the inadequately insulated air source heat pump scenario still had a reduction of 13%. In terms of the external wall transmitted heat losses, the results showed that when adequate insulation was provided alongside the heating systems, there was an annual mean 58% reduction in heat loss with reference to the inadequate insulation scenario, and this pattern was found throughout all months of the year. Okay, the findings for the three pairings of heating systems with different building fabrics respond to whether insulating building homes is a first option rather than initially looking to completely changing a heating system. The simulation results showed that the uptake of a more sustainable heating system, such as air source heat pump, may not always make less overall impact on the environment. In some months of the year, a gas boiler system equaled or even bettered the energy performance and carbon emission levels than that of an air source heat pump system with inadequate insulation for the building. Having a lack of adequate insulation was proved to be worse for the environment. The results presented in this study also reveals that the wiring with adequate installation was rather crucial on top of the improvement of heating system efficiency. Well, if we conclude this study based on the AES simulation for the multiple design options of a typical UK wiring with wiring strategies of gas boilers and air source heat pumps and the building fabric insulation pairings, the optimal design option was found from a sustainability and feasibility outlook. Basically, the results showed that adequate insulation was imperative to exercising an air source heat pump's maximum potential in heating the dwelling. Otherwise, the system might not be significantly better than conventional gas boiler systems. Specifically, the optimal design option could reduce energy consumption up to 53% and 40% of carbon emissions than the conventional methods during the heating period. This study somehow identified in the UK context conceptually preliminary solutions in addressing the gap between the adaptability of low carbon heating systems and uninsulated dwellings, which will dedicate to achieving low impact domestic heating and therefore ensuring residents' well-being in a sustainable way. Moreover, This study and its subsequent research can serve as a role model for the synergetic research and the development of low-impact domestic energy systems and housing retrofits within the Global South context in response to environmental deterioration globally. Thank you very much. Any questions?
Thank you very much, Liang, for the very interesting presentation. If any of the audience members has questions, please do post them in the Q&A box. I work in the area of retrofit, and often retrofit is overlooked when government policy champions the installation of technologies. People think just by putting air source heat pumps, we shouldn't really worry about insulation or anything, or poor performing homes. We can just put air source heat pumps, power them with some renewables, and all our problems will be solved. In your view, in light of your study, do you think that is a good way to be thinking about things?
Okay, thank you for the question. So basically, the reason, we're trying to produce the results is recently we had a workshop with industrial partners. They have a huge concerns about these kind of issues, lack of the thermal insulation, but they're trying to to replace and phase out the conventional means, but based on their actual performance. From their projects, they didn't receive the good results. If the the household, they didn't get enough insulated home, so they will pay more bills. So for instance, they have some evidence show that the system will run a longer period compared to the conventional boilers previously. Especially during some severe situation like extremely cold outside, so there might be some issues for the air source heat pump. In other countries, we know that in Canada, I know most of the air source heat pump is allocated underneath the basement, because in that country they have a bigger house and they have a basement normally, so they can deal with such issues. But in the UK, I think we still have some issues like most of the buildings, residential buildings, were built many years ago, and we have a limited space to to cover the outdoor units. That could be another issue. So that's why, certainly I think this is something really we need to pay more attention. Thank you.
Thank you so much. We haven't received any further questions, so I have one more question, and not wanting to put you on the spot. You mentioned that in the UK we have some space limitations for installing the outdoor part of an air source heat pumps. Are there any other limiting factors within UK houses internally that could limit the usefulness of air source heat pumps? So for example, where do we put the tank for the hot water heating that will be required? So we're replacing maybe combi boilers, which aren't very big, with a system that requires a hot water tank internally. How do you think UK homes would fare, or would there be any problems in UK homes?
Well, thank you. I think it's a really good question. Okay, so from my own point of view, basically, I can see that most of the UK residents, they just try to compromise the situation. So I just see a lot of my friends, their own houses, they in many of them houses, they get a boiler just installed, just in a corner of one of the rooms. That was very strange, for me at least. I seen a box just underneath. There will be a boiler or something. Sometimes it's pretty noisy. I think it's something we might come to the early design stage, especially in the future we might have communication with the between the engineer and the architects and even the civil engineers. We're trying to find out the solution. That would be more effective. Especially if you've seen that our results show that the uninsulated home, we need to, even during the summer months, even we use the air source heat pump, we still get a high amount of the energy consumption and consequently the more carbon emissions. So so it's really but the good thing is I already seeing improvement of the the benchmark and criteria, based upon the guidelines and the building regulations. So yeah, I think the next step that will be implement in the real projects. Thank you.
Thank you so much, Liang. It's always good to see how technological aspirations actually perform in reality, and a great study which exhibits that fabric retrofit is an important component in making technologies work. So to all the audience members, this was the last presentation of today's very exciting session. So I'll take a moment to just reflect on the interesting array of papers that my presenters today took us through, ranging from demand response, its acceptability and its impact on communities in India, to the impacts of using both heating and cooling technologies in different contexts, and what that does to the grid energy use. We were also taken through strategies for improving both the skills of people who are advising on the design, or the future designers who will be setting the pace for energy use and energy efficiency in homes, and the buildings themselves. So I thank all of my presenters today, Yashima, Srijit, Saba, Rajat, and Siliang, for their amazing efforts and for undertaking such important and pertinent research. We look forward to them being repeat presenters in future BSOs, and also discussing how their research has developed going forward. We are ending slightly earlier than scheduled, which I hope will give you the opportunity to perhaps pop into other sessions. Thank you all today for taking the time to attend this. Thank you.